When we talk about star-planet interactions, we are talking about close-in planets. I mean planets that have semi-major axis of less than about 0.15 AU. And in this talk, I will mainly talk about planets that orbit around main sequence late-type stars. There are three kinds of interactions that involve those planets. The first one is irradiation, and especially the extreme UV flux of the star can heat up the atmosphere on those very short orbits and eventually lead to the evaporation of the planet. And it has been observed for the WASP-12 systems, and there is also evidence that the system is actually shrouded in diffuse gas that is thought to originate from the evaporation of the planet, as you can see on this nice artist rendition, and its results from Carol Haswell. The second kind of interactions involve magnetic fields. And when the planet has its own magnetic fields, the short period means that it can orbit into the subalbanic regime and that it can lead to magnetic reconnections between both coronae. And it has been shown by simulations in the case of the system HD 189733. Cohen et al. Has done time-dependent MHD simulations that show that the reconnection of the magnetic fields of the star and the planet evolve in time as the planet orbits around. So you see here different phases of the orbit around the star, and this can explain variations seen in the light curves, and in particular the presence of hotspots regularly with the orbital period. So I won't dive deeper into the two kinds of interaction, and this talk will be mainly devoted about gravitational interactions that you have on those very short orbits. So we believe that they are very strong because the tidal torque scales as the semi-major axis to the -6. And what we know for sure is that close-in giant planets cannot form on those very short orbits. They cannot form there. They have formed beyond the ice line, and they have migrated. The mechanism through which they have migrated is not clear at the moment. There are several possible suspects. The classical one is, of course, planet-disk interactions, but more and more interactions have been evoked as planet-planet interactions, planet interaction with the planetesimal disk as the planet forms, and also the interaction with a distant stellar companion that can lead to the cosylid of cycles. Whatever mechanism is at play, and it's not maybe only one, it might be several at different stages of the evolution of the system. The idea is not to discriminate between one or the other, but to try and compare with the observations that we have what information we can gather on those mechanisms. And what we know is that the end of those of the migration is the beginning of tidal interactions. And tidal interaction has been known for a very long time. As John said, we are living in a binary system, and we actually experience the effect of tides on Earth. So there's been for a long time a theory that allows us to know the outcome of tidal interaction, and usually people use simple timescales to feel the effect of tidal evolution. The first one, of course, tidal dissipation will lead to, given enough time, the circularization of the system. And we can express this characteristic timescale of circularization with this nice formula that depends on the mass of the star, the mass of the planet, the radius of the star, the radius of the planet, the orbital period, the rotation period, some function of the eccentricities, and those Q prime factors that are tidal quality factors that have been measured actually in by observing the eccentricities of binary systems in clusters of different ages, and for the stars, and in the case of the planets, in our own solar system for Jupiter and its evolution with its moon, we can measure a Q prime for a giant planet. And also any initial obliquity between the stellar spin axis and the orbital angular momentum will get aligned through the action of tides, And we can express these characteristic timescales as is. And now there is a factor that it depends on the spin of the star, the angular momentum of the rotation of the star, and the angular momentum of the orbit. In the case of a hot Jupiter, this ratio is about 1. And the final effect of tides is the shrinking of the orbit, and that can lead in some configurations to the in-spiral of the planet into the star, and this happens on these timescales. So if I just use those simple formulae, and I use the systems, a typical hot Jupiter system with a solar-like star, a Jupiter-like planet, and I take the Q prime measured in the binaries for the stars and in Jupiter for the planet, I obtain those estimates. So the circularization timescale is very short for an initial orbit of 0.4, for example, on a Jupiter of 3 days period. The e-folded time is typically 4 megayear. The alignment timescale can be a little bit longer, but still smaller than the age of most of the host star that we observe. And the in-spiral time is actually worrying because it's very short, and those hot Jupiters cannot evolve toward a stable equilibrium, and they can only dive into the stars. So that means that we shouldn't observe a lot of hot Jupiters, actually. And what the observations tells us is that this is absolutely not what we observe. So here I put some plots of what we could find yesterday on exoplanets.org. So the crosses are the planets for which we have only the mass, so they are mainly obtained by radial velocities. And the dots are the planets for which we have both a mass and a radius, so transit and radial velocity. And the blue points are the Kepler results, and the red points are the CoRoT results. So here, if you look at this graph that is showing orbital eccentricity as a function of the semi-major axis, you see that even on those very short period, 3 days period orbit that is less than 0.1, you have a widespread in orbital eccentricity that wasn't expected with classical tide theory. And if you look at the spin-orbit misalignment measured for a few systems that we have as a function of orbital eccentricity, you see that we can observe a very wide spread in values, even at low orbital eccentricities in the misalignment, and even retrograde orbits, and no clear correlation with the spin-orbit misalignment with the orbital eccentricity. And finally, if you look at the planetary mass as a function of the semi-major axis, there again you see this cluster of massive planets of the mass of Jupiter orbiting on very close orbits with a typical time scale that should be very short. So what's wrong is, the question is really how efficient is the tidal dissipation is. And even though it has been measured in stars, there seems to be evidence that something else is going on with planets. So there's been a lot of efforts to put observational constraints on those Q prime values based on observation of exoplanets. I give a short list of paper here, and also a lot of theoretical efforts, because actually the missing link to know the tidal dissipation is really the main mechanism that is responsible for this dissipation, and it's related to the structure and the interior of stars and planets. And in the next talk by Stefan Mattis, you will have a nice detailed statement of the problem and the solutions. In the meantime, if I want to go back to comparing the observations with the migration theories, let's have a look at the eccentricity. And for example, in the classical in the classical migration scenario that involves interaction with the disk, we don't expect very huge eccentricity resulting from this migration. But we do see that closing hot Jupiters can have high eccentricities. Some of them are, of course, aligned, but circular, but some of them are eccentric. The question of the origin then led to this planet-planet scattering hypothesis, initially by Resier and Ford and those people, that I cannot say the name, sorry. And for example, Nagasawa et al. In 2008 produced results of N-body integrators that follow the evolution of multiple planets formed in a disk, gravitationally interacting with each other, and they actually can produce high eccentricity at the end of their evolution. And we reproduce the spread that is observed in the observation. The problem here is in the semi-major axis. If you look at the scales here, most of the planets that don't manage to reach the short orbital period where we observe them. In the same paper, actually, Nagasawa et al. Produced another model including tidal interaction with this N-body integration. And I will not share this result, but another paper that take on the same approach. And here we start with 4 planets in a disk, and we let them interact between them. And also we add tides when the semi-major axis becomes small. And with that, we can reproduce actually the global shape of what is observed with the short period planets on circular orbits, and then this nice envelope that we observe for the actual planets. Of course, there's this huge population of leftovers, remnants of the planets. So the colors of the dots are actually the number of remaining planets in the system after those interaction takes place. And here we don't have observation yet. We will have to wait for Plato to know if this population actually exists. But another worrying fact is this empty spot here in the simulation that cannot reproduce what is actually observed. We observe a spread in those what we call borderline planets, where the tidal effects could be strong enough to circularize or not the system. Also, with those simulations, by comparing the results to the observation, they could set a limit on the tidal efficiency in the planet to 10 to the 6, 10 to 7, which is about 1 or 2 order bigger than the one that we observe in Jupiter. It means tidal dissipation is actually less efficient in exoplanets. So about the spread, one hypothesis has been put out, and it involves the spin of the star. We know that those are late-type stars. They have magnetic fields, they have magnetic wind that are able to extract angular momentum from their rotation on long timescales, and their initial spin could vary, and the way they spin down could vary depending on the whole star, and that could reproduce this spread. So what's happening then if you include the angular momentum loss in the tidal evolution? Well, first, the evolution will still tend towards circularization and alignment of the system, but the shrinking of the orbit will be significantly affected. And actually, the driver of the shrinkage of the orbit is the resultant between the wind torque that acts to spin down the star throughout the lifetime of the system, and the tidal torque that can either spin up the star or spin down the star. And here I show you results of simulations that take into account tidal torque and wind torque, and it's just concerning the evolution of the semi-major axis. What I show here is the total angular momentum of the system, which is composed of the spin angular momentum from the star and the orbital angular momentum as a function of the mean orbital motion, which is the inverse of the orbital period. So that means that as n increases, the planet goes into the star. And here the solid line shows for each of this mean motion, for each of these orbits, the contribution of the orbital angular momentum to the total angular momentum. And the dotted line, the dashed line here is the locus of synchronization. So that means when the orbital period is actually equal to the rotation period, which is usually the place where tidal interaction stops. When you include my angular momentum loss from the star, there is no such equilibrium anymore because the star is continually spinning down. So what happens, and if I take, so those different points are different initial conditions of rotation period of the star and orbital period of the planet. What happens is that tidal evolution is completely impaired by the angular momentum loss, especially in the case of, so those three simulations are fast rotators, fast rotating stars, and then the wind torque completely overcomes the tidal torque, and the usual evolution, if the tides were the only one responsible, would actually, in this part of the diagram, lead the planet to evolve away from the star and to reach higher semi-major axis. On the contrary, what happens is that the evolution is dominated by the loss of angular momentum through the wind. The planet has no time to actually migrate significantly. It does, but you cannot see it here. And this happens until the system reaches the synchronization locus, where actually the tidal torque changes sign. And now the tidal torque acts to spin up the star, while the wind torque still spins down the star, and we have a competition between them both, and actually the wind torque overcomes the tidal torque until a precise balance between the orbital angular momentum and the spin momentum that is defined by this dotted line, which represents the locus where the tidal torque exactly compensates the wind torque. So this is for a usual Skubanich type law of magnetic braking. And while the wind torque compensates the tidal torque, the system can enter into a stationary state, and especially for this track number 5, you can see that the evolution proceeds along this state of balance between the tidal torque and the wind torque. And this actually acts to slow down the tidal decay. In this part of the diagram, the planet, if we don't consider angular momentum loss, would be driven into the star by the action of the tides very, very quickly on the timescale that I've showed you earlier. But thanks to this slowdown of the total torque, then the evolution of the system proceeds at a reduced pace. And eventually, while the tidal torque becomes stronger and the planet proceeds as an evolution that is mainly dominated by the tides, as usual, and leads to the destruction of the planet. This is the place of the Roche lobe where we consider that the planet is tidally disrupted. And this other one is the same thing, but with an F-type star and a slightly reduced prescription for the angular momentum. The global evolution is the same, but the actual places where this equilibrium, this stationary state can exist and how long it can be maintained is actually affected. The problem there is that the angular momentum loss seems to play a significant role. We don't actually know very well how it depends on the stellar parameters. We know by the observation of the rotation of G-type stars and F-type stars that they seem to have different laws for the angular momentum loss, but we are still limited by our knowledge of magnetic fields and magnetic coronae. But still, in principle, this could explain the spread in eccentricity, as has been first proposed by Dobson-Dixon in 2004. This could also explain the spin-orbit misalignment, and especially the correlation with effective temperature that you've seen a few days ago in Clément Baruto's talk. And of course, one way of seeing that is saying that tidal dissipation might be different for G-type stars and F-type stars, which is also relevant because we know that it's linked to convection and that both have different size of convective envelope. But actually, Rebecca Dawson recently proposed a new way of seeing things, and that the main parameter in this evolution is actually not the efficiency or the differential efficiency of tidal dissipation between F and G-type star, but their difference in rotational speed of the star and how it affects the tidal torque. And this could also explain the delay of tidal decay, just as I explained to you. In conclusion, understanding star-planet interaction is a necessary step to confront observations and predictions of formation and migration models. Not only that, but also when we can constrain these values with the observations that we have, we can also learn more about the stars themselves. For hard Jupiters in particular, around late-type stars, the magnetized wind torque can be comparable and opposite to the tidal torque, which leads to a significantly different evolution of the orbital parameters. And by providing accurate masses and radii and orbital parameters, CoRoT and Kepler have helped to put constraints on tidal dissipation efficiency and magnetic braking, both on the level of single system analysis and population analysis. Of course, we need better ages and stellar physics to understand exactly the dynamics of exoplanetary systems, and that's why we need Plato. Thank you.
Thank you, Cilia. Zvi.
A comment and a question. Thank you for this nice talk. I will present this afternoon maybe some evidence, very indirect evidence, probably, for star swallowing planets.
Mm-hmm.
So that's very interesting what you've shown. And the question I had, do you think it's possible that we observe now system with synchronized planets, namely that the rotation of the star is equal to the orbital period of the planet? Because I thought, yeah, right, this is impossible because of stability criteria, right?
Mm-mm.
Yeah. Okay, thanks.
Actually, we don't. If you compare, if you take the sample of the exoplanets that we know today and some estimation of the rotation period of the star, you see that most of them are not synchronized at all.
Well, there were a few papers where they thought that they measure the rotation of the star,
mm-hmm.
and it's equal to the orbital period. But I agree that this is impossible, right?
Mm.
Yeah, thank you.
Further questions, comments? Cilia, you discussed magnetic braking and said that it was less as you moved up to the F stars, but of course as you move slightly hotter, you get stars with extreme magnetic fields. And magnetic braking has long been discussed for those. Have you carried on up the main sequence to think about the braking in the very magnetic upper main sequence stars?
No. No, also because we don't have any exoplanets observed around those stars, or not many.
Right, if there are no further questions, let's thank Cilia once more for her review.